Okay, so I just want to quickly go through a couple of examples. These should only be like 10, 15 minutes each. So what we're going to do is we're going to load in, I think you've seen this, a truncated version of this data set before. It's called the Youth Survey data set. And let's just kind of have a look what's in this data set. And it's a mixture. Let me just get it up there. It's basically, I think it was a country in Eastern Europe. It was a lot of kind of preferences for different kind of types of music, genres of music. Here we go. Here's the actual data on the data set. So it's how you rate different types of music, movies, hobbies, phobias, health habits, personality traits, etc. There's also some demographic information. Now, what I'm trying to do is trying to build a model based on behavioral and psychological traits to predict gender. So to predict this. So I want to I'm going to do a k nearest neighbors, which is going to require quantitative predictors. And also this height and weight is kind of cheating, and the age is really just based on the sample. So I'll get rid of these columns as well. So literally, I'm going to try and create a a data set with all these psychological preference indicators and also kind of the gender. So let's do that. I kind of worked through which columns were which. And let's just kind of create my data. And this is just choosing the numeric columns. And let's just list them. The list.length equals 9999 just prevents str. str has a limit on the number of columns. I think it's about 50. But if we put list.length and we go up to 1,000, in this case up to 10,000 columns, this just tells us it lists us all of the columns. So here we go. Here's all the data. It's all these preference values of 1 to 5. And then we have gender at the end. So you can see here that there's some missing data. And this was actually one of the main purposes of this little example. I just want to show you how to do work with missing data. So the first thing is, if our dependent variable, gender, is missing, then obviously we can't really do anything. Our data is useful. So this is just saying if we only want the data where is.na is gender is NA. If we put an exclamation mark, this almost turns any kind of logical statement into a negative. So this is just saying where basically anything where the gender is not missing, remember we go rows, comma, columns in R, any rows where gender is not missing will return. So we're just literally, there was a few rows where gender was missing, so we'll kind of remove those. Now let's just see what we have in our data set, how big it is. So we can use n row. So we have just over 1,000 rows. Let's just look at the columns. Let's just see how much missing data there is. And this is just is.na, which items are missing. We can actually sum those because remember, if you've got a logical true and false, if you have false, it turns into a 0, and true is equivalent to a 1, so we can actually sum these. And then we just divide it by the amount of data. So it's rows times columns. So you can see we only have a very, very small proportion of missing data. If we just times it by 100, about 0.3, 0.4%. But let's just have a look. If we were to do complete cases, we only have 700 complete cases. So this missing data is kind of distributed. So if we just did complete cases, then we'd lose about 30% of the data, which we really don't want. So another way we can think about it is we can actually work out how complete each column is. Now this is actually, I've put this in, it's not that relevant for this data set, but if you have a data set where you have some columns that only have 20, 30% of the data, you might just want to get rid of them. Because trying to predict the missing data it just gets a little bit too complicated. You're not going to get too much useful information. So what we're doing here is basically we calculate the column sums, which are not NA. So this is this will actually tell you, this little bit of subcode will actually tell you for each of these columns how many pieces of missing information we have. And this was a survey. I guess this is going back a bit, maybe a pencil and paper survey, and some people just didn't fill it in very well. And then, we know how many actual rows there are, and we know what's missing, so we can say what's present. So this is the amount present. And then we just divide it by the total number of rows times 100%. And you can see we can get the percentage of data in each of these columns. Now here, we only have a few randomly missing values, but for some of you people, you have data sets with some columns that aren't good quality, have a lot missing. This is a way of getting rid of it. You would do col percent complete. And then you could actually say, okay, I only want to keep anything where the col percent complete. I only keep the columns where more than 80% of the columns are complete. Now I can do that here, and I'm going to return every column because every column has more than 80% of the data. So my data here is exactly the same as before. We still have the same number of columns that we did before, 135. Okay, so how do we actually kind of keep the missing data? Well, we basically have the last column gender, everything else is numeric. So I'm going to do numeric data is everything except the last column. And we could actually find the mean values, impute the means. So we'd find the col means for each column in the numeric data. Now in the book, they showed you how to replace a missing value with the mean values. Unfortunately, they did it with individual columns. So it gets a little bit much if it's a data set with, say, 100, 200 columns. So what I've done here is we have the mean values. And this isn't necessarily what I want you to do, but we have the mean values. What I'm doing here is I'm basically creating a matrix where I just have each of the mean values, I transfer it into a row. So I basically, for each of the columns, I take the mean, and I have basically put in the matrix the number of rows as well, if you did the help matrix command. You see the data, the number of rows, the number of columns. So I have number of columns minus 1. I have the mean values. And then I actually just repeat it across all of these rows. And by row just means I repeat downwards. So I take the means for each of the columns, and then I go kind of copy it by row, by row, by row, by row. And you can see here that we basically have a matrix that has, or a data set that just has all these means in the rows. And then all this is saying is if I have missing data, I replace it by what's in the replace vals, which is just the means. And then I create a new data set called my MI data. And I replace all the numeric columns with what I've just done, which is all the missing values returned to the means. And then if we had categorical data, we do something similar, but we actually just do it by the most common class. Now that's going to get a little bit complicated and repetitive. So what I recommend you doing is there's a package called mice, $mice. And what that will do is basically I run the mice function, I run it on my data set. Now basically what mice does is it kind of creates example data sets. It finds the distribution of the variables, and then it kind of tries to predict, based on a probability distribution, the values of the missing data. Now it will actually do it can do multiple predictions, each slightly different, using random numbers. But And what you might do is you might say, for example, take 10 of these and then utilize all of them in your analysis to try and get a big kind of metadata set. But that's a little bit complicated. So we're just going to make one prediction here. And you run mice. Now notice that I actually have a second line of code here. And this is if you're having trouble with mice, just try running this. I had to actually look online for this. This data set's fine, but I have a second data set where all the kind of predictions are incredibly correlated that mice has trouble. And setting these parameters is just a way for it to actually, I found, to work on that data set. So if this line of code crashes or doesn't get rid of all the missing data, then try this line of code. So we run mice, and I think we're almost there. It shouldn't take too long on a reasonable sized data set. Yeah, it basically usually does 5 runs on each of my imputations. So anytime now. And you basically run mice, create a mice object, and then your new data set is complete. And there we go. We have all the missing data replaced. No more missing data in my data set. Now we're going to do k-nearest neighbors. I didn't really focus on this in the k-nearest neighbors class, but when we calculated those Pythagoras or Euclidean distances, sometimes if some variables are on a different scale than the others, it means those variables are more important in the analysis, which is maybe not what we want. So this is the data set we created by replacing the means. And again, we're just going to scale all of the quantitative columns. And all that does is when we use scale, it just means we're going to subtract the mean and divide by the standard deviation. So we're basically getting z-scores for each of our data sets. Sorry, let's get above mean set. So here we go. This will show the first few lines. I think it could only actually show one line of this, but we could actually set. And let's just view this. And you can see here that all this data is just minus mean subtract standard deviation. Sorry, minus mean divide by standard deviation. Now, one thing is most of these variables are pretty much on the same scale of 1 to 5 anyway, so this might not actually be needed for this data set. But here we go. This is just the mean imputated data. And then standardized. Let's just get to the end of the data set. And there we go. We have the male and female at the end of the data set. And we do the same for the data set that we created with mice. Now let's just play around with carry. Let's just see which of these, whether the replacing the means or mice gives us the best values. So we're doing a bit of an experiment here. We're going to do k-nearest neighbors. And I did a bit of testing before. We're going to test values of k between 10 and 50. We're going to have train control. It's just going to return standard train control, repeated cross-validation. We're going to run it 10 times, repeat this 5 times, return the class probabilities. Again, the expand.grid, all that's saying is that we want to test it with values of k from 5 to 50. Sorry, from 10 to 50. And we're going to train on each of these different data sets. The ones where we replace the mean, the scaled ones where we replace the mean, mice replace the missing data, scaled mice missing data. Okay, let's run it. Okay, so it all worked. Let's just have a look at some of these models and what sort of results we got. So you can see here, the best value here for this one was case25, accuracy about 0.88. Again, 0.88. I mean, and to be honest, there was so little missing data in this data set. You can see this one has slightly better, but it could just be randomness. And actually scaling here actually worsens the performance a little bit. But again, this data set has very little missing data, so it's really not going to have a big impact on performance. Let's just have a look at the final confusion matrix. Let's just use this KNN fit 4. And we're comparing the predictions. If you recall, Carre returns this prediction table with predictions and observations. So we have prediction, 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 observation. Tell you what, let's just arbitrarily say that females is positive, as we have to give a positive class. And you can see here, overall, this is pretty impressive. You know, it's a 50-50 male-female, and we're about, 87% accuracy here. And we have quite a high kappa, predictions over random. And, it's not really biased in either direction. The errors of errors for males and females are very, very similar. The F1 metric we mentioned is pretty high. So overall, this was like really good predictions. Let's just play around and actually build a tree measure. So let's just do this, the data set we created with mice. R part, gender as dependent variable, and then all the other variables as independent variables. Let's just have a look what this tree does. I'll just show the first setting. Let's just run it. Okay, this was like kind of interesting. So this was going back to our data. This was how much you use PC. This is probably about 10 years old, this data set. So how often you use PCs, or how interested you are in PCs. So if you have high life struggles, you don't use PCs very much, and you like romantic movies, then 312 out of 337 are female. Conversely, if you have less life struggles, you like action movies, and you don't like reading, then nearly all of these peoples are males. Let's just have a look at an interior path. Yeah, so if you have high life struggles, you actually like PCs. So PCs are 5, but you don't like war movies and you don't like spending on gadgets. Then 25 out of 26 are female. Now it may be these complicated trees are a little bit overfit. So let's actually build an optimal. We'll optimize the complexity parameter as we did when we did the tree techniques. So let's just get all these different complexity parameters. And remember, the complexity parameter is how much increase we need before stop in kind of, relative of the misclassification rate. So how much, the misclassification rate needs to improve in order to carry on building the tree. So the higher the value of the CP, then the stricter we are and the smaller the tree. So let's just kind of build a grid with 20 different CPs, and let's just train and find the accuracy for each of these CPs. Okay, so in fact, if we look here, we can see that we have this kind of optimal accuracy about CP of 0.02, and then it kind of just goes downwards. So let's just have a look at the best fit tree. So we'd look tree fit, final model. We could actually show it. So let's just show what our final tree is like when we optimize using Carre. And you can see that this is a much simpler tree. The other tree was a little bit overfit. So we still have, you know, the best. It was so weird that PC is like, we've got all this movie and psychological data, dream data, and the best kind of classifier is like life struggles of whether you use the PC. So if you have high life struggles and you don't use the PC a lot, then nearly all of these people are female. You have low life struggles and you like action movies, then you're nearly all kind of classified as males. High life, but on the other hand, you could have low life struggles, don't like action movies, but if you also don't like celebrities, then you're liable to be male. So this was a much more kind of succinct tree. And let's just have a look at our confusion matrix. So you can see here the classification performance is not quite as good as the k-nearest neighbors. And as we said, tree techniques give a lot of interpretation, but they don't necessarily give the best prediction. So what do? We build some random forests. Now remember, entry is the number of features that we take in each of our little trees to build our forest. So, you know, we take 10 columns, 15 columns, 20 columns. We build a lot of different trees, in this case, the default 100, and then combine them. This is how many features we take. So let's just try a tree with 10, a tree of 15, and a tree of 20. We're going to take the complexity parameter we found for the previous pruning of the individual trees, and let's just run random forests on Carre. Okay, so let's just see what we get here. Again, this may be because of random error, because we didn't run that many repetitions, but we all get pretty good accuracy on the best one is M entry 10, i.e. 10 features. So let's just have a quick look at the confusion matrix. And you can see here, we get very good accuracy. If anything, slightly better than the k-nearest neighbors and certainly better than the individual trees. And again, but this time, interestingly, we get slightly higher sensitivity than specificity. We had females as positive, so this was actually slightly better at predicting females than predicting males. I'm not quite sure. I'm not quite sure why, but the overall accuracy was still pretty good on the overall tree method. Okay, so that was just an example. The purpose of the example was to show you how to use mice, how to scale the data for k-nearest neighbors, and also a bit more experience with kind of some additional tree techniques.